Hello everyone, and welcome to class number 27 of Physics 218. So, last time we continued our discussion of the infinite square well and its stationary states. In particular, we spent some time thinking about time evolution. If the wave function is a stationary state, you saw from our discussion and from looking at the PhET simulation that the probability density is constant in time. However, if the wave function is a superposition of stationary states, that is, if I have a wave function that's the sum of two different stationary states, then the probability density does vary in time. So you saw in the PhET and in Townsend how you get a probability density that just sloshes around if you combine two stationary states. Now, I introduced also last time the big question for us that we're going to continue working to answer today. And the big question is this. If I know what the wave function is at time t equals 0, how do I predict what the wave function will be at all later times? To give this a little bit of context, right? So suppose that I make a position measurement for a particle in an infinite square well. As we talked about last time, measurement is going to collapse the wave function to a really sharp spike. We want to be able to predict how that spiky wave function behaves thereafter. Okay, so in order for us to be able to do that next time, what we're going to introduce today is an analogy between wave functions and ordinary vectors in 3D that you know and love since Physics 117. And here's the kicker for today. This is the punchline. It's a really big idea. Frankly, in all of physics, that any arbitrary wave function for a particle in an infinite square well, and in fact more generally for any wave function, it can always be written as a sum of stationary states. So we'll spend today unpacking these ideas, but since we'll be thinking about vectors, I want to start us off with a clicker question to warm up. So, the clicker question asks you to think about the dot product of these two vectors, A and B, that are perpendicular. Now, hopefully you'll remember that the dot product of two perpendicular vectors is always 0. Now, if you want a reminder of how that all works, one way to think about it is remember that I can always write the dot product in terms of the magnitudes of the vectors and the cosine of the angle between them. Right? That's magnitude of A times magnitude of B times the cosine of the angle phi between the two vectors. Now, if for two perpendicular vectors like we have here, right, this angle phi is 90. So if A and B are perpendicular, phi is 90 degrees, and as you know from high school trig, right, the cosine of 90 degrees goes to 0. So therefore, A dot B equals 0. Okay, so this is a good reminder of an idea we're going to return to in a little bit. So I now want to begin the discussion of the analogy between vectors in 3D and infinite square well wave functions. I'm going to do this using a little bit of the language of linear algebra. If you haven't studied linear algebra, that's perfectly fine. But if you have, hopefully some of the ideas we're going to talk about today will start to sound a little bit familiar. So the first thing I want to introduce with thinking about 3D vectors is the idea of a basis. Right? So the idea is that for any 3D vector, right, I can always write it as some linear combination of vectors that are called unit vectors. Right? So let me draw you an example. Right? So let me just draw some axes here. So, right, so let me label a few ticks here. Right. So if I have a vector that looks like this, so suppose it's 3 units horizontally, right, and 2 units vertically, let me call this A for not being too creative. I can always write A in the following way, right? I can write this as the sum of something times a unit vector that points in the x direction. And so here it's 3. And then it's 2 units vertically, so I can plus a unit vector that points in the plus y direction. So let me label this unit vector in direction, and this is in plus y direction. Right? So more generally, right? So any 3D vector can be written in this way, and if you want to sort of see this a little bit more differently, right, I can draw this like this, where I have 3 times a unit vector in the x direction plus, adding tip to tail, 2 times a vector of length 1 in the y direction, so 3i hat plus 2j hat. More generally, in 3D, I just need 3 basis vectors. So, in general, I can write any vector in terms of our unit vectors I hat, j hat, and k hat. K hat being a unit vector in the positive z direction. Right? What we say is that I hat, j hat, and k hat form a basis for 3-dimensional space. Look for and if you want to be formal about it, right, mathematicians call 3D space R3. In a very similar way, it turns out that we can think of the stationary states of an infinite square well as forming a basis. Okay. Similarly, we can say that the stationary states of an infinite square well form a basis as well. So let me write that down. So stationary form a basis turns out for the space for all possible wave functions that are normalizable and can exist in an infinite square well, namely that they vanish at 0 and L. And now, I'm not going to try to prove right now that this does form a basis, but we'll sort of see how that is plausible as we go through the rest of today's class. So the next thing I want to talk about in this analogy between vectors and wave functions is this idea of the dot product. Now, the dot product for ordinary vectors goes like the following. So if I have vector A equals AX I hat, where A sub x is the x component, plus A sub y j hat plus, and I'll just write it on the next line, A sub z k hat, and B takes the same form, bxi hat plus byj hat plus b sub z k hat, then I can write the dot product A dot B just by multiplying adjacent the x components, multiplying the y components and the z components, and adding them up. So I get ax bx plus a y b y plus a z b z. It turns out we can define something that's analogous to this for wave functions. And what we might have is, so what we really should call this is, the formal mathematical term for this is an inner product. But you should really just think of this as a generalization of the ordinary vector dot product with which you're very familiar. So what I mean by the inner product is the following. And so let me sketch two different wave functions for you. So here, let me put L here. So let me imagine that let me just draw one bump here. So let's consider just, doesn't have to be, but let me consider the n equals 1 stationary state, and here the n equals 2 stationary state, just like this. Now, I know that these are really continuous functions between 0 and L, but maybe it's not going to be too much of a stretch to imagine that I can describe a continuous function like this by telling you what its value is at a whole bunch of points. So, to maybe first approximation, right, I can describe this wave function by giving you its values at a whole bunch of different x values. So maybe I know it there, so that's, I'll draw a dot, and I know it there, and there, and there, and there, etc. In a similar way, right, I can do the same thing over here, right? I can say I know this wave function here to, let me keep drawing a few more dots. I think you get the picture. Let me call this let me just call this an arbitrary function f of x and g of x here, just f and g being arbitrary names like a and b here. Right? So if I can write, f, I can almost imagine that I write f as a sort of a vector, right? I can just write it as a whole bunch of values at the various points. So I can write it as like f1 here, right? So that first value, and then like f2, its value at the next point, f3, dot, dot, dot. And similarly for g, I can write that as like g1, g2, g3, and dot, dot, dot. And I think you could imagine that, as I increase the number of points I describe my function at, I'm going to get a better and better representation of my actual continuous function. But writing f and g in this way, where I'm just listing out their components, sort of in the same way that I could write vector A and vector B by just listing their three spatial components, this kind of suggests how I might be able to get something dot product like. So I want something like having f1 g1 plus f2 g2 plus f3 g3 plus dot, 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 right, going on. Well, it turns out that the right way to do this, because the one other wrench I haven't thrown in here is that we have to remember that in general both f and g could be complex. And so it turns out that the right way to generalize this is to imagine a sum where I'm adding up points that are sort of closer and closer together. And if maybe you take a guess, it's going to turn into an integral. So the correct generalization is the following. Well, I'm gonna just roll over to here. This is one of the days I wish I had a bigger board, but we'll just have to make do. The analogy, the sort of analog of the dot product, or inner product between f and g, is going to look like the following. It's going to be the integral between 0 and L of f star times g dx. And hopefully you can sort of see the kind of parallel here, like I'm multiplying the associated components of my two functions together and then adding them up. Similarly, with the real definition of my inner product here, I'm taking my f at some value of x, really, well, if it's complex conjugate, multiplying with g, going to the next value, right, multiplying f star in g, and I keep going, and I'm summing that up for all the values of x between 0 and L. So this is my definition of the inner product between functions f and g, which is analogous to my vector dot product. So the next idea I wanted to introduce is something I call orthogonality. For 3D vectors, this means the following, right? So it means that if I have two of the same unit vector and I dot them together, right, I always get 1. So I hat dot I hat equals 1. Similarly, j hat dot j hat equals k hat dot k hat, they all equal 1. But if I take two different unit vectors and I dot them together, their dot product is always 0. Just like in the clicker we did at the beginning, right? If I have two perpendicular vectors, their dot product always vanishes. So I hat dot j hat equals 0, and we could similarly form any other combination, right? So I have I hat dot k hat equals j hat dot k hat. Those are all 0. Now we've just talked about how, right, I can think of stationary state wave functions as being like the I hat, j hat, k hat. And we just defined this funky inner product with an integral that I claim is analogous to the dot product. Well, this turns out to exhibit exactly the same kind of orthogonality property. So for stationary states, right, what we have is the following. If I have two of the if I have the same stationary state, right, so if I have psi n star, so let me just label this psi sub n of x, psi n star, psi n of x, dx from 0 to L, right? This is none other than our normalization requirement for stationary state wave functions. Right. Psi star psi we know to be the probability density, and we know if we have a particle in the well, the total probability between finding it finding it between 0 and L has to be equal to 1. What's new here is that it turns out that 0 to L, so if I have two different stationary states, so if psi m star of x and psi n of x dx equals 0, it turns out to equal 0 if m is not equal to n. So it may not be obvious why this is the case. Hopefully you can see the parallel. So like again, if I'm dotting two of the same unit vector, I get 1. If I'm inner producting two of the same stationary state, I get 1. I dot together two different unit vectors, or inner product two different stationary states. So here psi sub m is some other stationary state. It turns out I get 0. Now it may not be obvious why this is true in all cases. What I want us to do now is there's a handout with an exercise that helps you see why this is true graphically in one particular case.